I'm Tang. In this video, I'll present our work on multitask reinforcement learning for quadcopter attitude stabilization and tracking using graph policy. Controlling the quadcopter attitude normally involves two key challenges. First, aggressive stabilization from arbitrary states like recovering from free fall. Second, smooth tracking of target angles. But with current RL framework, it is difficult to design a single reward function that works well for both stabilization and tracking. Given this example, the reward function that aims to minimize tracking error and improve action smoothness. For the aggressive control task, we need W1 equals to 0, whereas for smooth control task, it is desired to have W1 greater than 0. Thus, our goal is to first develop a multitask DRL approach to handle multiple control tasks simultaneously. Second, develop a control policy that is compact enough to deploy. To achieve this goal, our first ingredient is a graph convolutional network, GCN policy, that encodes structural knowledge about the interrelationship between the state, task, and environment. The second ingredient is a highly parallelized simulation environment based on Isaac Gym that captures high-fidelity dynamics. This enables fast training, around 10 to 20 minutes to converge, and result in a deployable lightweight policy. Here we introduce our GCM policy. The GCM policy takes the state, user-defined tasks, and the environment latent variable in order to produce the actions. The GCM policy treats this input as nodes in the graph. Connections or edges between nodes are learned, but we also initialize them based on domain knowledge like decoupling yaw from pitch control. This effectively reduces gradient conflict and speed up learning. Interestingly, the learn adjacency matrix reveals how GCM policy encodes the relationship between the nodes. For example, row state has a stronger relation with the row action, pitch to the pitch action. And interestingly, yaw state has almost no correlation to the yaw action. Likewise, we can color more edges and it becomes obvious how each node contributes to the final actions. Yeah. That is satisfying. The resulting graph is complex but entirely incredible. Cool. To bridge the gap between simulation and real world, first we apply domain randomization to vary dynamics like mass, wind, thrust, and torque, etc. in simulation and provide these privileged information to an encoder that generates environmental variable for our GCM policy. Then in the second training phase, an adapter tried to reproduce these latent variables from history buffer without privileged information. At runtime, only a small adapter runs, predicting environment latent variable from recent state action history. Here's the training footage. Each episode, total number of 57 tasks, including stabilization and tracking, are assembled uniformly and assigned to each simulation with randomized dynamics. I only show 50 simulation here so I can render it. It takes around 36 minutes to complete. In practice, I normally train with 1,000 environment without rendering, and it takes around 10 minutes to complete. After training, we test in Isaac Gym and Gazebo before real-world deployment. In attitude tracking tasks, the agent follows row pitch yaw command accurately and remains stable even under slight disturbances. In stabilization tasks, after rotor shutdown and free fall, the GCM policy successfully recovered from extreme angles and high angular velocity in all 13 trials. While our graph-based policy performs excellently for quadcopter control, it may not be suitable for every robot due to its simplified and restricted representation. Still, doing multitask training is highly recommended. There are many benefits. First, you obtain improved sample efficiency via enhanced exploration and progressive learning. Mastering running is probably easier after walking is learned, right? You may also grant your policy multitask capability, improve its representation, and avoid overfitting and such. And best of all, It comes for free. No additional computation is required. And that's it. Code is provided in the link below, and I hope you enjoy and have a wonderful day.